Hi, my name is Mehmet Burak Aykenar. I work at Roketsan Company in Turkey. I graduated from Middle East Technical University in electronics engineering. In my master thesis, I studied implementation of filter architectures on GPUs and FPGAs and evaluation of their performance comparisons at TOB University. Now, I'm a PhD candidate in Ankara University Electronics Engineering Department. I'm working on implementing estimation algorithms efficiently on FPGAs and heterogeneous architectures like Xilinx Zynq SoC. I hope you will enjoy my presentation, and I'll be glad to answer your questions in question and answer sessions. Thank you. So our presentation is called a multiple model approach for estimating roll rate of a very fast spinning artillery rocket. Me and Caner, we work at Roketsan Company. Professor Soysal and Professor Efe, they are affiliated with Ankara University in electronics engineering. So our outline is the artillery rocket systems first. I'm going to introduce, then our flight test and our data acquisition system. Then I'm going to talk about roll rate and roll angle analysis and the measurement system, the roll rate estimation with our multiple model approach coming later, and I am conclude with the results and the discussions. So what are the artillery rocket systems? They are mostly unguided, they have fixed wings, and they have the spinning for the stability, but due to the unguidance they have higher CEP. You can fire multiple rockets to suppress enemy lines, and they have the usually salvo capability. It is possible to add guidance and control to lower the CEP. So why you can add guidance to a rocket? Because you can fire less ammunition and you transport less firing vehicle to the operation area. Cost-effective guiding methods emerged after the operation of Desert Storm in 1991. How can we add guidance and control to a conventional or unguided rocket? The conventional method using an IMU, a GNSS 4DC motor. The advantages IMU and GNSS are not very expensive and easy to obtain, and 4DC motor you can control 3 axes. However, gyroscope scale factor increases with high spin rates due to accumulation, and controlling 4DC motor and their circuit expensive. So we propose 2-axis magnetometer, a GNSS, and 1 DC motor. So magnetometer is cheaper than IMU, and in magnetometer there is no scale factor error because you don't accumulate the data, and 1 DC motor and motor control circuit is cheaper and less complex. So we conducted a flight test and we acquired the data of the flight test. Our rocket is 122 mm grad type artillery rocket, and our target is at 28 km. We use 2-axis magnetometer to measure roll rate and the roll angle. We have the GPS receiver, and we use 2 GPS antennas because our rocket is rotating. Data encoder and the telemetry transmitter. Again, we have 2 telemetry antenna. So how we get the information from the rocket? We have 2 telemetry receiver systems in the ground, and we have a radar to track the rocket, and the radar drives the telemetry receivers. And when we get the flight information, the data, we analyze the roll rate by differential equation. So this is the famous Newton-Euler equation for the rate. So if you do the calculations, and the details are in the paper, we have this differential, first order differential equation of the roll rate. So what are the unknowns? Okay, the inertia of the rocket we have, and the diameter and the surface area. So here is the dynamic air pressure. In order to calculate dynamic air pressure, you need altitude and the velocity information, which we get from the GPS receiver. And the CL and CLP, they are the dimensionless aerodynamic coefficients, and these values change according to Mach of the rocket. So we calculated, actually we get those numbers from the DATCOM software, and the velocity we also get it from the GPS receiver. In order to analyze and simulate the roll rate of the differential equation needs to be converted to the difference equation. And when we use this difference equation, we get this roll rate during our 61 seconds flight. So in 2 seconds, the rocket engine just burns out and the rocket achieves nearly 10,000 degrees per second roll rate. Then it drastically reduces and it has a nearly steady state condition up to the end of the flight between 4,000 and 5,000 degrees per second. So how can we measure with 2-axis magnetometer the roll rate? So there are the Z and Y axis and they have 90-degree phase difference. So our distance, the change, it is the 90-degree, and the speed we need to calculate, and we know the time. So if we take 0 crossing times for the y-axis and the z-axis, so we can take the difference of T2 and T1. So we know the time difference, we know the angle difference, so we can calculate the roll rate. So here are the results. So the red is the measurement from the 2-axis magnetometer, and the blue is our difference equation model. So we can see up to 9 seconds, 10 seconds. The model and the measurements they comply each other. But after that, the model just have very different behavior than the measurement. Also, we see that the measurement has a very noisy output. So in order to analyze the filter output and evaluate our estimator, we need a Bayes data creation algorithm, because we have only one flight test, but we need some numerous test simulations. So first we create a Bayes ground data. So we use the 5th order polynomial fit for every second, so it's equals to 400 sample. Then we put this output to a moving average low pass filter to smooth the data. So here is some interval of our generated data, the red line, from the real data. And for the noise parameter, we didn't use, of course, one simple mean approach, because the behavior of the data, the behavior of the measurement is very different, as you see, at different time intervals. So we evaluate these variances for different intervals. So we calculated them and we add as a Gaussian random variable as a noise parameter. And we did 50 Monte Carlo run for the filter results, for calculating the root mean square error, of course. Okay, we designed 3 Kalman filters, and the first one is that related to our difference equation model, and it's a two-state Kalman filter. And the second one is the non-Wiener acceleration model Kalman filter, and it has 3 states. And the third filter is the integration of first and the second filters, first and second models with IMM algorithm. And the details of the IMM algorithm can be found in our paper, of course. Due to the limited time, I need to skip the details of the algorithm and the results. Okay, the difference equation Kalman filter, as we remember, it fits to the model, the real results at the 9 or 10 second. But then the results are not perfect, and the Wiener acceleration has better results in the steady state part of the flight, but it has worse results for the high variance part of the flight. So when we integrate these two Kalman filters, we have exactly better results at each time than the measurements, except for the first 2 seconds, which is the initial burnout of the fuel. So other than that part, our results are better than the measurements. Thank you for listening me. Due to the limited time, I only try to emphasize our insides of the paper, our work. You can find more information in our paper. You can ask any question in question and answer session, or you can email me anytime, and I will be glad to answer. Hope you enjoy your Fusion conference. Thank you.